to this lecture, even if you're meeting under very unusual circumstances, but basically this is what it is. So I'll be presenting this lecture entitled Simple Harmonic Motion and Forced Vibration. So basically we are going to see what simple harmonic motion is and why do we have to do forced vibrations. So basically simple harmonic motion, we are talking about vibrations. What are they? Okay, so the way we are going to do that, we are going to go through the frequency, the velocity, and other things, position, velocity, acceleration, and stuff like that. Our study of simple harmonic motion is going to be quite specific mass, which is attached to a spring. So like in this particular case, where is that? Here. So here we have a surface, this mass, this spring, we've got a spring and you've got a mass. The spring is this zigzag thing which you have there. Then this spring is attached to a wall. So the spring, one end of the spring is fixed, okay? The other end of the spring is attached to the mass. Then this mass, which is attached to the spring, is on a surface, okay? In our tomb, this surface on which the mass is on is very, very, very smooth. Basically, the surface is what we are trying to call something frictionless. It doesn't have any friction. Okay. However, the idea that you have a surface which does not have friction is not true, because friction, whether very, very little, is always present, and friction opposes the motion of objects. That's why when something is moving, it always comes to a stop. So us assuming that we have a mass which is on a frictionless surface is actually us trying to make life very, very simple for ourselves, because friction brings about a bit of a complication, as you are going to see. Okay, now we are looking at simple harmonic motion. The reason why we are looking at simple harmonic motion is because a lot of things exhibit this kind of motion. This simple harmonic motion, a lot of things exhibit this kind of simple harmonic motion, and that's the reason why we're looking at it. There are people who, Tumba, Kayombo, can you click on your microphone? Yes. So many objects, many systems exhibit simple harmonic motion. And what is simple harmonic motion which you're talking about? Basically, simple harmonic motion involves an object going back and forth about a fixed a position of equilibrium. Okay, for example, if you, this mass which you have, okay, if you leave the mass and the spring to their own selves, the spring is going to push the mass up to a point where it's comfortable. Everybody is comfortable with each other. If you try to squeeze the spring is going to be unhappy about what you're trying to do. So instead, what the spring is going to do is going to push the mass. If you give the two of them a bit of time, the spring and the mass, they will come to an agreement on where everybody is supposed to be. So the spring and the mass will agree to say, okay, fine, the mass is supposed to be at this particular position and the spring is supposed to be extended or compressed like this. So everybody at the end of the day is going to be happy. That is what we call a position of equilibrium, where the mass finds where it's supposed to be and the spring is also happy about where the mass is. However, if you try to extend the spring by pulling the mass, or you try to compress it by pushing the mass, then you let go, the mass will start moving back and forth. The spring will push the mass, it will go beyond the equilibrium position, then it will pull the mass, it will go beyond the equilibrium position. So the spring will keep doing this pushing and pulling against the mass. So the mass keeps on going back and forth about an equilibrium position. This kind of motion where you have an object going one side of the equilibrium position and then the other time is going to the other side of the equilibrium position, going back and forth like that about this equilibrium position. This kind of motion is what we mean by simple harmonic motion. A very good example of simple harmonic motion is a simple pendulum. On a simple pendulum, you have a string attached to a clamp or whatever it is, or either the string is attached or you're holding the string in your hand. Then at the end of the string there is a mass attached to that end of the string. Then if you do not do anything, the mass and the string will come to an agreement on where the mass is supposed to be. That is the position of equilibrium. Okay. On the other hand, if you move the mass sideways slightly, then you let go, then the mass attached to the spring will start swinging back and forth like that. That is another example of simple harmonic motion. Simple harmonic motion is by nature, it is repetitive. Then this repetitive motion happens about a fixed position. Another example of simple harmonic motion is when you are trying to push your little brother or your little sister on a swing. Okay? The swing is an example. When someone is on a swing, they are going back and forth about an equilibrium position. Before you put your little brother on a swing, the swing was in a particular position where you found it. That position in which the swing was in, that is its equilibrium position. The swing is happy in that position. If you sit on the swing, no one pushes you, the swing will be in that same particular position. However, if someone decides to push you from the back, then you're going to go forward, then you come back, bypass that position, which is the equilibrium position, to the other side, then again you come back like that. So you start going back and forth like that. This is what we refer to as simple harmonic motion. Okay? Simple harmonic motion is also sometimes called vibrating. Something is vibrating or something is oscillating about in position. Okay? If there is no friction, like in the case of our surface here, if there is no friction, then the mass is going to go one side, some particular distance, then compress the spring, then the spring will be unhappy, the spring is going to push the mass to the other side again, the spring will be extended like that, so the distance is going to be the same on both sides of the equilibrium position. Basically, that's what happens when there is no friction. However, that is not usually quite realistic, but for purposes of what you're trying to do, that is fine. So, the distance from the equilibrium position, the position of equilibrium, that equilibrium position is what we denote that as x equals to 0. Then any distance from the equilibrium position, x equals to 0 is the equilibrium position. If you notice, I've highlighted that. Then any distance from the equilibrium position is basically, it's either for you to have, if you're not from the equilibrium position, it's either you stretch the spring. When you're stretching the spring, then if you assume that the spring obeys Hooke's law, the spring is not going to be happy about you stretching it. So it would try to unstretch itself. So it's going to set up a force inside the spring, which is going to be opposites the force you're using to stretch the spring, and that force is what is known as the restoring force. When you let go of the mass you have stretched, the spring is going to pull back the mass. Okay? The spring is pulling back the mass, trying to bring it to its equilibrium position, because your action of stretching the spring set up a force inside the spring which is equal but opposite to the force you have applied. That is basically the statement of Newton's third law of motion. If you apply a force on something, that something you have applied the force on is not going to be happy about your actions. It will try to apply an equal but opposite force. So in our case here, when you stretch, you pull the mass, so that the spring stretches. The spring is going to be unhappy about your actions. So the spring is going to set up a force inside itself, which is going to pull back the mass. So the moment you let go of the mass, you see that the mass moves to the other side. It gets pulled by the spring. Okay? As the mass is being pulled by the spring, the reason why the spring is able to pull the mass is because there is a force which has been set up inside the spring due to your action of extending the spring. The force which has been set up inside the spring depends on how much the extension is. That's where Hooke's law comes in. The amount of extension you have caused the spring to extend by, which is equals to x, the displacement, times something called a spring constant, k. So the extension is the x multiplied by something, a physical quantity which springs have, called the spring constant k, is equals to, when you multiply the spring constant times the extension, it gives you it will be equal to the spring constant, which is a property of the spring, times the extension which the spring undergoes. The product of the spring constant and the extension will be equal to the force which you have applied. This force which you have applied inside the spring will set up a restoring force. The restoring force inside the spring, the force through which the spring pulls the mass, will be equal but opposite to the force you have stretched the spring by. You used to stretch the spring. Basically, that is an effect of Newton's third law of motion. When you let go, after you pull the mass to one side, or you compress the spring, you push the mass to one side. It's either you pull the mass or you compress the mass to one side. Then you let go. Your pushing force or your pulling force stops existing. You pull the mass. By you pulling the mass, you end up stretching the spring. When you stretch the spring, the pulling force exists. Okay? When you let go, the pulling force disappears because you're no longer pulling, you're no longer stretching. However, the fact that you stretched the mass, which in turn you pulled the mass, the fact that you pulled the mass, which in turn stretched the spring, that set up a force inside the spring which is known as a restoring force. This restoring force will not disappear just because you are no longer stretching the mass. It is this restoring force which the spring uses to pull the mass back, but as the spring tries to pull the mass back to its equilibrium position, the mass will not stop at the equilibrium position. The mass is going to go beyond the equilibrium position. Okay? The mass ends up going beyond. So basically, this is what I'm trying to say here. At this position where the mass and the spring are happy with each other about where they are, that is the equilibrium position, x equals to x naught. Then you decide to pull the mass by a distance x from the equilibrium position. Your action of pulling the mass from the equilibrium position will stretch the spring, and the spring is going to be unhappy about this stretching which you have done. Okay, so this action is going to set up a force inside the spring which will be pulling in the opposite direction of where you're pulling. So the moment you let go, so this force F equals to kx your pulling force disappears, then this force, F is equals to minus kx. The F is equals to minus kx exists because of Newton's third law of motion. For every action, there is a reaction which is equal but opposite. So inside the spring, there is this force F is equals to minus kx. So when you let go of this mass, it will start moving this particular direction. It will be pulled by the spring. So the mass will be pulled by the spring. It will approach this dashed line here, which is the equilibrium position, but the mass is not going to stop here. The mass will go beyond this side. When the mass goes beyond this side, yes?
Yes, what does x mean?
X is the displacement, the distance from the dashed line, this dashed line, the extension.
Oh, thank you.
Yeah, how much the spring is going to extend. Okay, so when you let go of this mass, because you're pulling the mass, when you let go of it, the mass will be pulled by the spring, the other side. So this mass will slide, it will approach the equilibrium position. But when it approaches the equilibrium position, the mass will go to the other side. So basically what the mass does, it will start compressing the spring. Okay? This other side, when you pulled ourselves, we're extending the spring. When the mass goes to the left hand side, it will start squeezing the spring. When the mass starts squeezing the spring is going to be unhappy about the squeeze which is happening. So the spring will start pushing the mass in the opposite side, in the opposite direction. So as the spring starts pushing the mass in the opposite direction, and the mass is squeezing the spring, eventually the mass will come to a stop for a short time. Okay? As the mass comes to a stop for a short time, the restoring force is now going to be opposite. That restoring force is going to push the spring to the other side. So as the mass, the restoring force in the spring is going to push the mass to this other side. So the mass again will start approaching the equilibrium position. However, as it approaches the equilibrium position, it will not stop at the equilibrium position. It will go to the other side. So basically the mass again will start stretching the spring. Okay? So the movement of the mass to the right will stretch the spring. The movement of the mass to the left will squeeze the spring. So the stretching and squeezing of the spring will set up restoring forces which will keep on pushing the mass to the left and to the right. Hence, even without you touching the mass on its own will start moving back and forth like that. This kind of motion is what we refer to as simple harmonic motion. Okay, so basically, which is causing the force which is causing this mass to move back and forth is the restoring force, and the restoring force is minus kx. So since that is the restoring force which is causing that, we can write Newton's second law of motion, the famous Newton's second law of motion. F is equals to kx. F in the Newton's second law of motion is the force which is causing the acceleration. M is the acceleration being caused. So in this case here, instead of F here, we're going to replace the F with minus kx. Okay, so we end up having minus kx is equals to M, the mass, times A, the acceleration, which is what we have here. F is minus kx, which is the force, then the mass times that, the acceleration. So we can actually make the acceleration, because we're always interested in the acceleration, we can make the acceleration the subject of the formula by dividing by m on both sides. So if we divide by m on both sides, we end up having A is equals to minus k over mx. So basically, for a simple harmonic oscillator where a mass is attached to a spring, we end up having the acceleration to be equals to minus k divided by mx. The next thing we do is we let this k divided by m to be equal to omega. W omega squared. We let k divided by m to be equals to omega. Omega is what we use for angular velocity. The same symbol for angular velocity. As you're going to see, basically, that's what's happening in a nutshell. So if k over m is equals to omega squared, then omega is going to be equals to the square root of k divided by m. This omega is what we call the natural frequency or the natural speed. Okay? The frequency at which something is vibrating on its own without being forced to do anything, the natural frequency of the spring mass oscillator. So the natural frequency omega is equal to the square root of k, which is the spring constant divided which is attached to the spring. This omega is yes.
Yes. Why is omega equal to k over m?
Why is omega equal to k over m? Omega squared. Omega squared is equals to, we let to be equals to k over m. This is behavior which has been observed really. We do this every time we're dealing with a simple harmonic oscillator. So that's a step we take. We let omega squared to be equals to k over m. The omega itself is actually the vibration, how something is vibrating on its own. Or you notice something that not the vibration, or we can say the speed. You will notice that this mass keeps on going back and forth like that. Okay? How many times does it go back and forth? It's going back and forth, passing some particular. It's like it's moving in a circle. It's doing the same thing, going this side, coming like that, back and forth like that. So that's what that omega is. So we let omega be equals to omega squared be equals to k over m. Then omega in turn will be equals to the square root of k over m. And omega is what we call the natural frequency of an oscillator, spring mass oscillator. Then omega is also related to the frequency. Omega is related to the frequency as follows. Omega is equals to 2 pi times f. F is the frequency. So we can actually get the frequency. If we make the frequency f the subject of the formula, we end up having frequency is equals to omega divided by 2 pi. Like that. Now, 2 pi, if you remember your circular motion, 2 pi is actually an angle. If you remember circular motion, 2 pi is actually an angle. It is an angular distance which you cover when you move in a circle. So if you move in a circle, the distance you cover if you move in a circle is what you refer to as 2 pi. Okay? So, what does this tell us? It is telling us that the frequency of our oscillator is related to the distance you move in a circle. Okay? And omega, which is our natural frequency, is actually, to be is actually the angular velocity. When something is going back and forth about an equilibrium position, it is equivalent to going in a circle, something which is moving in a circle. When something is moving in a circle and something which is going back and forth, as far as physics is concerned, they're the same. Okay. So that's how we get our frequency. Our frequency is equals to, there's frequency, there's natural frequency. The natural frequency is omega, which is the angular speed. The natural frequency, as you can see from there at the top, natural frequency depends on k, depends on m. The natural frequency depends on the spring constant, it depends on the mass. This quantity of natural frequency does not change. For a particular mass and a particular spring, the natural frequency is always the same. It's a square root of k divided by m. it will not change with time. That's why we call it the natural frequency. It won't change. Okay, that natural frequency is related to the frequency. If you count how many times your mass is going back and forth about a particular position, that is the frequency. It's related to the frequency using this formula. Omega is equals to 2 pi f. Therefore, you can work out the frequency to be equals to omega divided by 2 pi. There is another physical quantity which is related to frequency, which is the period. The period of an oscillator, how many times an oscillator is going back and forth, how many seconds does it take the oscillator to go this side and come back? How much time does it take? That is what you call the period of an oscillation. The period of an oscillation is measured in seconds. The frequency is measured in hertz. The period of an oscillation is denoted tau, is given by tau is equals to 1 over the frequency. The period of an oscillation of an oscillator is the reciprocal of the frequency. That's how we find the periodic time. Okay, there. Equation number 7. Tau period is equals to 1 over f. So if we ask you to find the period, meaning the time it takes for you to do one complete oscillation or vibration, basically you can find that tau is equals to 1 over f, which is that. The next bit is what? Just a minute. Okay. So if tau is equals to 1 over f, here we know f is equals to omega over 2 pi, right? F is equals to omega over 2 pi, that is equation number 6. Then tau is equals to 1 over f. Therefore, it means that tau, which is a period, is equals to 2 pi over omega. This 2 pi over omega, like that. However, from the top here, we know that omega is equal to the square root of k over m. So if we substitute omega there, we end up having tau is equals to 2 pi, then the square root of k over m, which gives us tau is equals to 2 pi, the m comes on top, we end up having m over k, like this. This is how the period, how much time it's going to take an oscillator, is related to the natural frequency, like that. It is time. For you to work out the time, basically that's what you do. Basically you divide, for you to find the time, you divide the angular distance divided by the angular velocity, like that, equation number 8, and that gives us equation number 9. So that's how you work out the time. Okay, so these bits, I've introduced them. How do you work out the period? How do you work out the frequency? What is the natural frequency? How do you get the frequency? Now let's get back to here. Where are we starting from here? This equation number 3. A is equals to minus k over m, then x. Then if we have done what you have done here, omega is equals to the square root of k over m, then basically what we have here is this k over m is actually omega squared. This omega squared. So this k over m can be replaced by omega squared, and that's what we do. So we replace k over m by omega squared, this side. So we end up having A is equals to omega squared x. That. Yes, sir.
What are you doing? You're not by yourself.
I am teaching my first years.
You mean your family back from South Africa?
No, the first years.
You are lonely, you are working too hard. Oh, so you are people now.
Yes.
Come and see me tomorrow, right?
I'm teaching first years online.
Okay.
Yeah. Okay. Oh, let me admit one of your friends. Okay.
So could you please re-explain how you got to the A is equals to omega squared x?
How do I get to, okay, so it's up here. Up here. We have this. A is equals to minus k over m x. then we do this. We let k over m be equals to omega squared. This. So k over m is basically equals to that, omega squared. That's what we have there. So basically, I rewrite the same equation in terms of omega squared. Okay. So when I do that...
Okay, thank you. I've understood.
Alright, that's good. So when I do that, I have a is equals to minus omega squared x. Okay. Now, I start doing something. I want to express my acceleration in terms of... I want to express a in terms of x. Okay. Now, the first thing I do is I know how to work out the velocity. For me to work out the velocity, I need to find out the distance which has been covered divided by the time which has taken place. That's how you work out the velocity, right? Velocity is equals to the distance covered divided by the time taken. That is the equation number 11. However, if I want to work out the acceleration is equals to the change in velocity divided by the change in time. That is the acceleration. The acceleration is equal to the change in velocity divided by the change in time. Basically, the final velocity minus the initial velocity divided by how much time it has taken. Okay. But if you look up here, I have something which looks like velocity. So I get this v, I replace it here. When I replace the v there, I end up having change divided by the time when it's on. Then inside, I place this. I put delta x, I put delta t. When I do that, this triangle, the change, is going to multiply by this with this triangle. So I end up having triangle squared x, then I end up having these two guys, 2 delta t's squared like this. Then if I put this back, when these things, these triangles, they change, the triangle basically means change. Okay, when the change becomes very, very, very small, when the change becomes very, very small, you end up having your triangle becomes a D, like that. It becomes a D. This must be something you have seen in mathematics. If you have been doing your calculus, there's a derivative, first order derivative, like you're doing dy dx. Then if you do the dy dx again, you end up having d squared y dx squared, which is basically the same thing we're doing here. That's what you end up having. So basically, for you to get the acceleration, you need to differentiate. What this is telling us here is to say, for you to get the acceleration, if you have the distance covered by some object which is moving, then you also have the time it took. Okay, for you to get the acceleration, you need to differentiate the distance, which is the x, once. When you differentiate the distance, you get the velocity. Then you differentiate the velocity again, you get yourself the acceleration. Okay, when you do that, basically, so this is a fancy way of writing, a highly mathematical way of writing the acceleration. You can write your acceleration in terms of the derivative of x with respect to 2 twice. You get this thing, you put it here. You end up having d squared x dt squared equals that. Then you get this negative part, you bring it here. Now, this thing which you have here is very complicated mathematics for a first year, and that's what we call a differential equation in mathematics and in physics. These differential equations, they show up a lot. However, we are not going to solve this differential equation. What I'm going to give you is the solution to this equation. Okay? I will not solve it. You are not required to solve this thing. What I'm going to give you is the solution to this equation. Every equation has got a solution, and that's what I'm going to give you. Okay. So you do not need to know how to solve equation number 15. or equation number 14. The only thing you need to really understand, is that the acceleration can be written like this, as shown in equation number. The acceleration which you have been working out can also be written as shown in equation number 13. Then you do the substitutions. If you substitute equation number 13, you substitute it in equation number 10. So you end up getting this guy in equation number 14. Then this negative part of equation number 14, you bring it to the other side, you end up getting this equation. And this equation is a differential equation. You do not need to know how to work it, because I'm going to give you the answer to this equation. I'm going to give you what x looks like. So for this particular differential equation, the x is the solution to this differential equation is this one. X is equals to x naught cos omega t plus epsilon. That is the solution to that differential equation. X is the position. X is the position. X naught is the maximum. X naught is the maximum displacement. X naught is the maximum displacement of the mass from its equilibrium position. When you pull, remember you have this. You have this. When the mass and the spring are very happy with each other, this is what you have. The mass is at its equilibrium position. So when you put the mass to one end like that, the maximum you have put the mass, the maximum extension from the equilibrium position, that is the x naught. The maximum extension from the equilibrium position, this is this x naught. This one here. That's what this is. X naught is the maximum extension from the equilibrium position, and it is given a special word name. It's called the amplitude. Just a minute. Yeah, it's called the amplitude. This omega, we already know. Omega is the natural frequency. Omega is the square root of k divided by m. T is the time. Then this last bit here, this last bit is what we call the phase. Usually the last bit, that E is equals to 0. So basically most of the time it doesn't show up anywhere. So here, these are the explanations. X naught is the maximum displacement of the mass from the equilibrium position, and we call that maximum displacement the amplitude. Omega, this one omega, is the natural frequency of the spring mass oscillator. Omega is equal to the square root of k divided by m. That's what omega is. How fast this spring mass oscillator is going in a circle. You can look at the whole thing as going in a circle. The small e is what's called the phase angle, and most of the time, basically at first year, the phase angle E is just equal to 0. So basically it doesn't really show up going forward. So basically going forward, our solution x, our x is equals to x naught cos omega multiplied by t, equation number 17. Someone wants to be admitted, or someone has left. Okay, which is our equation number 17 there? Just a minute. My computer needs time to respond. Okay, just a minute. Ready to respond. Just a minute. Okay, here we are. All right, so this is the solution when your oscillator, the X is the solution when your oscillator is moving on a floor. Okay, it's moving on this frictionless floor. However, it is also possible that you can have a mass which is hanging on a spring. Okay, in that case, if your mass is hanging on a spring, then the solution is still the same. The only difference really is, instead of X, you end up having Y. Then instead of Y naught, X naught, you end up having X naught. The solution is the same. Everything else is the same. Again, this is a Y. This Y naught is the amplitude. Then you've got cos, then omega t, like that. So, we know how to do differentiation. If this is the position, if you differentiate that, you do a derivative. Velocity is equal to dx dt. This is how you get the velocity. You differentiate the x with respect to t. So it will be d dt, then inside where there is x, you put this guy here. Okay? This amplitude does not change, but if you differentiate cos omega t, when you differentiate cos omega t, you get minus sine omega t. Then if you differentiate this guy inside, you get omega t. So basically, when you do a derivative, you get your velocity. Your velocity becomes equals to minus omega x naught sine omega t, like that. That is how you get your velocity at any point. If you want to work out the acceleration, you have to differentiate the velocity with respect to t. So if we do that, acceleration is going to be dv dt, to be d dt, then where there is the v here, we put this guy there, and we differentiate with respect to t. This is a constant, then we differentiate this guy, we differentiate sine with respect to t. When you differentiate sine, you get cos. So you get cos, then inside the cos, the sine, there's omega t, you differentiate that again, you get omega, so you end up having omega squared, then x naught cos omega that. So basically, from this, x omega t, x is equal to x naught omega t, you get your velocity. Your velocity becomes this minus omega x naught sine omega t. So you multiply by something, and there's a negative there. Then if you want to get the acceleration is going to be minus omega squared x naught cos omega t, which is this. The other thing you notice here is there's a time. So basically, there's a change. Cosine functions and sine functions change with time. And that is exactly what happens in our case. Yes, that's what happens in our case. So the value of the acceleration, the value of the velocity, the value of this x, they are going to change because this guy is changing. It's a cosine. It changes with time. The velocity is going to change because this guy is changing. The acceleration is going to change because this guy is changing. So, simple harmonic motion is one of those few examples of motion where the velocity is changing, where the position is changing, the velocity is changing, the acceleration is also changing. The acceleration is not constant. It is also changing. So if you want to get maximum displacement, maximum velocity, maximum acceleration, then this guy, this cos omega t, should be equals to 1. This sine omega t should be equals to 1. This cos omega t here should be equals to 1. that is when you get maximum displacement, when cos omega t is equals to 1, when sin omega t is equals to 1. When these guys become equals to 1, this bit is equals to 1, then your x becomes x naught. Basically, you get maximum displacement. Then here, when this one is equals to 1, sin omega t is equals to 1, then you get maximum velocity. Maximum velocity becomes equals to minus omega x naught. When cos omega t becomes equals to 1 here, then you get maximum acceleration. Maximum acceleration becomes equals to minus omega squared x naught. This we know how to work out. This is the amplitude. So basically you get your x max. X max is equals to x naught. Y max is equals to y naught. Maximum velocity is equals to minus omega x naught. For you to get maximum, this bit I've highlighted has to become equals to 1. For you to get maximum acceleration, this cos omega t needs to be equals to 1. Then you get this. Minus omega squared x naught becomes equals to 1. That's what you get there. Okay. So, but that's the case there. So we look at an example. Okay. We look at an example, and this example is going to help us understand basically what's happening. Okay. So the example 1, very, very useful. It helps us understand that. So a particular spring stretches 0.2 meters when a 0.5 kg mass is hung from it. So if a spring stretches 0.2 meters, when you hang a mass of 0.5 meters, it means that you can find the spring constant from that information, because the 0.2 meters is the extension, and the 0.5 meter, the 0.5 kg times acceleration due to gravity gives you the weight. So you can use that information to get the spring constant, and that's what we're going to do. Next, suppose that this mass, the 0.5 kg mass, is replaced by a 2 kg mass, and the system is then vibrated horizontally as shown in here. We vibrate the system. Is it here? Where is that? Let me see. Oh, no. Up here. Like we had here. Where we started here. So this one, you replace the 0.5, you replace with the 2 kg mass, then you pull it, then you release it, then it starts going back and forth like that. So basically it starts carrying out simple harmonic motion. Okay. So suppose this mass is replaced by a 2 kg mass, and the system is then vibrated horizontally as shown by displacing the mass 0.4 meters from its equilibrium position and releasing it. Find the spring constant. So in this case, when the spring was attached to the 0.5 kg and was let go, the spring stretched. Then it had the spring, the 0.5 kg mass, and the 0.2 extension. The spring was happy. So using that information, we can get a spring constant. However, when we attached the 0.2 kg mass, then we stretched, we displaced the mass to a distance of 0.4 from equilibrium position, then we released it, it starts vibrating. Okay, so the first thing we need to do is you need to find the spring constant. For us to find the spring constant, we have to use Hooke's law. According to Hooke's law, F is equals to Kx. So we find K to be equals to F divided by X. So in our case, the F which stretched the spring the first time around was 0.5 times 9.8 meters per second squared. Basically the F is 4.9 newtons. Then the extension, which was caused by this 0.5 kg mass, the extension was 0.2 meters. So using the force of 4.9 newtons and the extension of 0.2 meters, we can work out the spring constant K as K is equals to the force divided by the extension, which is the 4.9 newtons divided by the 0.2 meters, like this. So we get a spring constant K of 24.5 newtons per meters. So this is our spring constant for the spring. This is a spring constant for the spring. The next bit is we replace this 0.5 mass with the 2 kg mass. We replace the 0.5 kg mass with the 2 kg mass. When we replace the 0.5 kg mass with the 2 kg mass, we can next work out the natural frequency. Because why I work out natural frequency is because when we replace the 0.5 kg mass with the 2 kg mass, we vibrate. We put the 2 kg mass up to a particular distance, then we release it, then it starts vibrating, going back and forth. So we can actually work out the natural frequency. The natural frequency omega is equal to the square root of K over M. K is what you have found here, 24.5 newtons per meter squared. M is the mass when this mass is vibrating. We have attached the spring. The mass we have attached to the spring is a 2 kg mass. This mass, the 2 kg, we have attached a mass of 2 kg to the spring, like that. So we work out omega being equals to basically this. Omega is equal to 24.5, then divided by 2 kg, whatever we get, which is this, then we square root, we get omega is equal to 3.5 radians per second. Now, omega is equal to 3.5 radians per second. Now, radians per second are units for angular velocity. The velocity of something which is moving in a circle. That is what radians per second is. Radian per second is the unit for angular velocity. So, what this means is that according to physics, when a mass is attached to a spring and it's going back and forth, when a mass is attached to a spring and it's going back and forth, it is as good as that mass which is going back and forth is actually moving in a circle. Like it's being, like when you attach something to a string, then you rotate it, you make it move in a circle. That's basically what's happening. Like that. It's going back and forth. It's as if something is moving in a circle. And that's what these units are telling us. Our natural frequency is actually the angular velocity. When something which is moving in a circle, you look at it from the top, it appears as if it's just going back and forth, like that. Okay? The next bit is the frequency. How do you work out the frequency of vibration? We know that this guy, the angular or the natural frequency, is related to the frequency like this. Omega is equal to 2 pi f. Therefore, if you want to find out what f is, we make f the subject of the formula. We get f is equal to omega divided by 2 pi. We have omega. Omega is this one, 3.5 radians per second divided by 2 pi, which is that. So f is equal to 3.5 radians per second divided by 2 pi. So we end up having a frequency of 0.557 per second. This 0.557 per second basically is the same as frequency is equal to 0.56 hertz. This guy. This is our frequency of vibration going back and forth. This frequency of vibration, we can use it to find the periodic time, the time it takes our mass to go back and forth and come back. We know that the periodic time tau is equals to 1 over frequency. So basically this is equals to 1 over 0.55 hertz, which gives you 1.78 seconds. Basically that is a period, like that. Now, I want to show you how the position changes as a function of time. This is a plot showing that. When you plot this, the maximum position is 0.4. So when you pull your mass from the equilibrium position, when you pull your mass from the equilibrium position, it will have a displacement of 0.4. When you let go of the mass, the spring is going to pull the mass. So as time passes, this is a time, a graph of time and position. So as time goes, this is over a period of 5 seconds. What's going to happen over a period of 5 seconds? Someone is trying to enter a meeting or what? So over a period of 5 seconds, when you release the mass, after you have pulled it from the equilibrium position, you have put it a distance of 0.4 meters, which is 40 centimeters, slightly more than your 30 centimeters ruler. Then you release, you let go. The spring is going to pull the mass towards the equilibrium position, like that. So the distance from the equilibrium position is going to reduce from 0.4, it will become 0.3, it will become 0.2, it will become 0.1, it will become 1, it will become 0. However, like I've said, and as you might have noticed, the mass is not going to stop at the equilibrium position. It's going to go to the other side. The mass will start squeezing the spring. It will go to the other side, a distance of 0.1, 0.2, minus 0.3, minus 0.4. These distances are negative because we are talking about displacement. But as the spring is being squeezed, the spring will be unhappy about the squeezing which the mass is doing. So the spring will start pushing back. Because the spring is pushing back, eventually the mass will come to a stop at minus 0.4. When the mass comes to a stop at 0.4, the mass is not going to stay there because the spring is unhappy about being squeezed. So the spring is going to push the mass. So the mass starts moving again from maximum. It will be at minus 0.3, minus 0.2, minus 0.1. It will come at the equilibrium position, but it will not stop there. It will go to the other side. So basically, when it goes to the other side, the mass starts stretching the spring all the way up to maximum, and it will stop. As the spring is being stretched, the spring is unhappy about being stretched. So the spring tries to pulling back. Okay? Eventually, the pulling of the spring will make the mass reach maximum position. When the mass comes to a stop there, it will be pulled back again, like that. So basically, this pulling and squeezing, so the mass here is being pulled by the spring, then it will reach equilibrium position, then it will go beyond the equilibrium position, the mass will start squeezing the spring will become upset because of its being squeezed, then the spring will start pushing the mass, like that. It pushes the mass, then the mass is going to pass through the equilibrium position, then as the mass goes to the other side, the mass will start stretching the spring. The spring will be unhappy for being stretched, so the spring will start pulling the mass back again. When the spring is pulling the mass back, the mass will come like this, like that. It will come to the equilibrium position, then to go beyond, then the mass will start squeezing the spring like that. It squeezes the spring, then it goes to the other side. The spring will be unhappy about being squeezed, then the spring will start pushing the mass like that. So basically, this whole thing is going to happen, and you can see it looks like a cosine wave, like that. And that's why this x is equal to x naught cos omega t has got cosine in it, because the movement of the mass back and forth about the equilibrium position looks like a cosine function when you measure the time. Okay. If we plot on the other side, we try to plot the velocity. So in our case, our x max is this. That is the x max, and that's what you have. When this part becomes equals to 0, your x max is that, and that's basically what you have here, maximum displacement. So, on the case of the velocity, when you have put your mass to maximum position there, it's at maximum position, your mass is not moving. Therefore, the velocity of the mass is equals to 0. However, when you release the mass, the velocity will start increasing, okay? But the velocity will start increasing in the direction opposite to where you're pulling. Is that clear? The velocity, you're pulling in one direction. When you release the mass is going to go in the opposite direction. So it's going to gain velocity in the opposite direction. Okay? So the velocity is going to increase in the negative direction, negative to the direction in which you're pulling the mass. So the velocity is going to increase in that particular direction. Then the velocity is going to be maximum here. This position maximum here, between 0 and 1. Between 0 and 1, if we go back to the position, the plot of the position, somewhere here, between 0 and 1. Between 0 and 1 here is just here. There. The time between 0 and 1 is there. This is when the mass passes through the equilibrium position. So when the mass is passing through the equilibrium position, the mass has got maximum velocity. The velocity is maximum when the mass is passing through the equilibrium position. That is why the mass does not stop. The mass does not stop because when it's passing through the equilibrium position, it has got maximum velocity. When it goes to the other side of the equilibrium position, that mass will start squeezing the spring. When it's squeezing the spring will be unhappy about that. So the spring will start pushing against the mass. That is the reason why the mass, the velocity of the mass starts reducing until it becomes 0. There, velocity in meters per second. It will start reducing until it becomes 0. It will become 0 on the other side. Here, just near to 1 second here. If you go to the position graph, near to 1 second, just near to 1 second here, there. You can see it is on the opposite side. It has reached maximum position on the opposite side. That's where the velocity becomes equals to 0. After becoming equals to 0, which is where we have here, the velocity is going to increase because the spring is being pushed, the mass is being pushed by the spring. It will be pushed in the opposite direction. It will be pushed in the opposite direction and the velocity is going to increase. Again, the velocity is going to become maximum when it's passing through the equilibrium position, this particular point. Somewhere between 1 and 2. But near at 1, somewhere here. Near at 1. And you can see that is this position. Equilibrium position is there. There. That particular position. When it's passing through this particular position, this is the same position here. There. Your mass has got maximum velocity. So basically what you see here is that every time your mass passes through the equilibrium position, it has got maximum velocity. Then when it goes to the other end, when it reaches the other end, the velocity becomes 0. Then it will be pushed again, it will be pulled, then the velocity starts increasing. Then when it passes through the equilibrium position, it will have maximum velocity going this side. Then as it goes beyond the equilibrium position, it starts squeezing the spring will becomes unhappy, the spring is pushing against the mass, the velocity of the mass reduces, it becomes 0 on the other end. And on the other end, when it becomes 0, again the mass is pushed by the spring, the velocity starts increasing. When it passes through the equilibrium position, the velocity is maximum. Then as it goes beyond the equilibrium position to the other side, the mass starts stretching the spring becomes unhappy, the spring starts pulling the mass. The pulling of the mass by the spring reduces the velocity of the mass, the velocity becomes 0 until it stops on the other end. When it stops on the other end, the spring continues to pull the mass, so the velocity starts increasing. When it passes through the equilibrium position, the velocity of the mass becomes maximum. It goes to the other side, the mass starts squeezing the spring becomes unhappy, the spring starts pushing against the mass. When the spring is pushing against the mass, the velocity of the mass reduces until it becomes 0, like that. So basically this is what happens, and this is how the velocity of your mass changes. The velocity of your mass will constantly change during this whole process. It will be maximum when it's passing through the equilibrium position, and it will be minimum, it will be 0 at the ends where the displacement is equal to maximum. The other thing is, so basically your maximum velocity, if you want to work out the maximum velocity, you have to make this guy to become equal to 1. We set this guy to become equal to 1, then we'll remain with this. So your maximum velocity, when it is passing through the equilibrium position, is going to be equal to omega, which is 3.5 radians per second, times the displacement, which is 0.4 seconds, and there's a negative there. The velocity, yes?
Sorry, why are we equating the sine omega t equals to 1 again?
Because we want maximum velocity. Sine,
so are we always
sine has
supposed
got
to equate it to 1?
Sine has got a maximum. Sine and cosine have got a maximum at 1. The maximum value a sine and the cosine can have is 1. That's why we are equating it to 1. At any other point, yeah, it's less than 1.
Okay.
So we get your maximum velocity as this. So it will be minus 3.5 radians per second times 0.4 meters, and you get your maximum velocity like that there. Another interesting thing is you could try to figure out how the acceleration is changing. Okay, the acceleration changes like this because the acceleration also follows a cosine thing, but except it follows a cosine but a negative cosine. So the acceleration, the other thing with cosine is position. The position has got a cosine, right? This cosine, like this. But imagine you've got this cosine, then you put a negative, because acceleration has got a negative. So basically it becomes the opposite of this thing. It flips upside down like this. If you put a negative sign here, this cosine becomes upside down. So when this thing becomes upside down, what it looks like when it becomes upside down is this. It flips like this. And that's how your acceleration is going to change. And again, similarly, if you want to find out your maximum acceleration, which is what your people are interested in, you set your cos omega t equals to 1, and therefore your acceleration in this case becomes a max is equal to minus omega squared x naught. So the omega squared like that, then the x naught is a displacement, you do that. So your maximum acceleration is going to be minus 4.9. Now, the one thing you notice here, maximum acceleration is equals at 0, there's maximum acceleration. At somewhere close to 1, there's maximum acceleration. Somewhere at the end of 2, near to 2, there's maximum acceleration. The maximum acceleration here, there. The maximum acceleration corresponds to positions of maximum when there's maximum displacement. When you've got maximum displacement there, you've got maximum at the time when you've got maximum displacement, that's when you've got maximum acceleration there at 0, just slightly close to 1 second there. Maximum acceleration happens when you've got maximum displacement. When maximum acceleration happens when the mass is changing the direction in which it's moving. So if it's going one way, when it's changing that direction, when it's changing the direction, it's going this way, it stops and starts going the other way. That point when it's changing the direction, that's where maximum acceleration happens. Okay? And that's a point where you have maximum displacement. So basically, yeah, that, and here we have got these graphs. These graphs, all the three graphs which you have, the one for velocity, the one for position, the one for velocity, the one for acceleration, we have put them together in one plot, and you can see what's happening. The blue one is the one for displacement. That's how the displacement is changing. The orange one is the one for velocity. That's how the velocity is changing, like that. The one for the green one is the one for acceleration. So you can see the time you have got maximum displacement there, that is the time when you've got maximum acceleration here. Okay, so every time you've got maximum displacement, you've got maximum acceleration. When your displacement is equal to 0 here, your acceleration is also equal to 0. This side here, you've got maximum displacement, you've got maximum acceleration there. This side there, you've got maximum displacement, you've got maximum acceleration here. This side here, you've got maximum displacement, you've got maximum acceleration here. There, you've got maximum displacement, you've got maximum acceleration. So, maximum acceleration happens when you've got maximum displacement, because it's only when you've got maximum displacement that's when the direction in which this particular object is moving is going to change. Okay, like that. So basically that's what this thing is showing. Okay, these other bits, okay, 4 pages. Now, energy which is stored in a simple harmonic oscillator. Now, when you squeeze a spring, or when you stretch a spring, what you're doing is you are storing energy in that particular spring. And the energy you store is what is called elastic potential energy. When you squeeze a spring, or when you store a spring, when you squeeze a spring or you stretch a spring, you are storing energy in that spring. That spring is what is called elastic potential energy. Okay, and the elastic potential energy which you have stored when you stretch a spring or you squeeze a spring is equals to half k x naught squared. This is the elastic potential energy. Okay. However, things don't always remain, your spring will not always remain stretched, because we know that if this spring is attached to a mass, then you release the mass is going to move. As the mass is moving, it has got kinetic energy, but also the amount of stretching is reducing, so there is still some potential energy there. So the total potential energy, actually, the total potential energy is equals to a combination of some potential energy plus a combination of kinetic energy. That's what the total potential energy is. The total potential energy is a combination of some potential energy plus some combination of kinetic energy. The total potential, the total is this one, half kx naught squared equals to half kx squared. The potential energy at a displacement x plus the kinetic energy. There is half everywhere, so you can cancel out the half. When you cancel out the half, you remain with kx naught squared equals to kx squared plus mv squared. There is this guy. This guy has got k and has got x. You take it to the other side, so you end up with m squared. mv squared is equals to kx naught squared minus kx squared. You factor out the k. When you factor out the k, you end up having mv squared is equals to k x naught squared minus x squared, like that. You divide both sides by m, you end up having v squared is equals to k over m, which is equals to bracket x naught squared minus x squared. However, then you square root on both sides. If you square root on both sides, you end up having v squared is equals to the square root of k over m and this. Then this square root, you can spread it out across these guys, you end up having v is equal to the square root of k over m, then the square root of x naught squared minus x squared. This guy, the square root of k over m, we know that is equal to omega. So you end up having omega is equal v is equal to omega the square root of k over m, like that. Basically, this is how you get your velocity of the mass. The velocity of the mass is equal to the square root of k over m, then inside the brackets, the amplitude squared minus the displacement where the mass actually is. That's how we get the velocity of the mass at any position. That's how we get the velocity of the mass at any position. If the position is x naught at the equilibrium position, the stretch, the extension is equal to 0. So you see that if x is equal to 0 at the equilibrium position, this equation gives you a maximum value of velocity. This is the reason why we are saying at the equilibrium position, the mass is going to pass through the equilibrium position with maximum velocity. Okay. Now, these things, damped and undamped, damped and forced oscillations, usually, in reality, the amplitude of your spring mass oscillator, this one which is stretching like this, is not going to be the same, because eventually the amplitude, as it's going back and forth, is going to die down. So the amplitude of your spring mass oscillator is going to reduce with time, and when it reduces with time, what you end up having, you're going to have a situation like this. As time goes by, the amplitude is going to reduce with time, like that. Eventually the back and forth thing is going to end, or is going to die down. So basically, the size of the amplitudes as time passes in reality dies down. Okay, this situation happens because there is friction between where the mass is passing and the floor on which it's passing. The surface on which this thing is passing and the mass, there's a small amount of friction there. And that is a friction which leads to loss of energy. Friction eats up the energy. When you squeeze, when you stretch your oscillator, you are storing energy there. The energy you store is equal to half k mv squared. However, because of friction between the mass which is passing on the floor and the floor, that friction is going to lead to a loss of energy. If you get your hands, you rub your hands, try to rub your hands, you will feel that your hands become hot. Okay? The reason is because friction eats up energy, and that energy is transformed into heat. So basically, the potential energy which was stored in the spring, because of you squeezing the spring, that potential energy is going to be lost. As the potential energy is being lost, the amplitude to which the spring can be stretched reduces the time. And that's the reason why you have this. This is the reason why this thing happens. The reason why this thing happens is because the first time you stretch the spring, you store a certain amount of energy in the spring. The energy you store is equal to half k multiplied by the amplitude. However, because of the presence of friction between the mass and the surface on which it's moving, that friction is going to eat up, slowly but surely, it's going to eat up all the potential energy. The fact that potential energy is being eaten means that the mass can no longer go to the previous amplitude. So as time goes by, the amplitude to which the mass can actually go to is going to reduce. This kind of motion, where there is friction, that is what is known as damped vibrations. However, there are three types of damped vibrations. There are vibrations where you have got a very small amount of friction. If you have a very small amount of friction, then this is where you have this blue line. You're going to have, your amplitude is going to reduce like that. However, there is another case where you can have a certain amount of friction where the red line, from the amplitude, your thing just comes to a stop, like that. This is what is known as critical damping. In the case of the green line, you have got so much friction that the mass does not go back to its equilibrium position. In the red line, the mass from the displacement, from the amplitude where you have stretched it, the mass goes back straight to the equilibrium position. That is what is known as critical damping. When you have got over damping, the mass actually fails to go back to the equilibrium position. It actually fails most of the time. So these are the three types of dampings which you have. So, if, for example, you put your young brother or young sister on a swing, then you push him or her on a swing once, okay?
Sir,
Yes.
kindly repeat on the types of damping.
There are three types of damping. There is under damping. When something is under damped, when you stretch the spring, then you let go. When you stretch the mass is attached to the spring. Then you let go of the mass. So what's going to happen is the mass is going to approach the equilibrium position, but it will not stop at the equilibrium position. It's going to go to the other side. That mass is going to compress the spring. The spring will not be happy. Then it will push the mass. It will go back beyond the equilibrium on the other side. But when it goes to the other side, you look at the amplitude. The amplitude has reduced. So every time it passes the equilibrium position, the amplitude reduces. Eventually it will come to a stop. So basically this is under damping, the blue line. There's very little friction such that the mass can go beyond the equilibrium position to the other side. With critical damping, the amount of friction is not little, but again, it's not too much. The amount of friction is not too little, it's not too much. It's just enough that when you release the mass goes straight to the position. Okay? That is critical damping. Once, just straight to the equilibrium position. In the case of overdamping, there is so much friction that the mass attached to the spring struggles to go back to the equilibrium. It doesn't even reach the equilibrium position. It will try to go back, yes, but it won't even reach the equilibrium position because the friction is too much. So in the case of overdamping, the mass does not return to the equilibrium position. In the case of critical damping, the mass goes straight once to the equilibrium position. In the case of overdamping, the mass keeps on shooting over the equilibrium position until after some time it gets back to the equilibrium position. That's the difference between the dampings. The different types of dampings are controlled by how much friction is present. If there is very little friction, you have got under damping, which is the blue line. If you have got a certain amount of friction, but it is not very little, then you end up with critical damping. Then if you have a certain amount of a huge amount of friction, then the mass will not be able to go back to its equilibrium position, and you have what is known as overdamping, which is what you have there. Okay. So mostly what happens, even when you're vibrating a mass attached to a spring in air, air offers a certain amount of friction, very little. Okay. So basically, in the case of air, you are vibrating stuff in air, you end up having something called you have underdamping like that. Is someone trying to enter this? If you run out of data, it's fine because I'm recording this. You can always watch it anytime, and it's going to be put on YouTube, so you can download it. Okay. The next bit we're going to look at is something called a forced vibration. Now, forced vibration, you do forced vibrations because you realize that in the reality there is always a small amount of friction, and that friction is going to reduce the amplitude of the vibrations. For example, if you put your little brother or your young brother on a swing, then you push them, okay? Then you don't push them again. With time, the amplitude where the swing, how far the swing can go back and forth, it's going to reduce with time. Eventually, it's going to come to a stop. So if you want a system to continue vibrating with maximum amplitude, you need to keep on pushing. You need to keep on pushing. When you are pushing, then you have got this back and forth. If you've got a back and forth motion, which is a result of a force being applied, then that is what is known as forced vibrations or forced harmonic motion. Okay? You need, for you to have maximum amplitude, you need to push with a frequency which is equal to the frequency of the system you're pushing. Okay? When the frequency with which you're applying a force, F, is equal to the frequency with which the system naturally vibrates, then your system, you're going to have maximum amplitude. Okay? And that's how you're going to get things. When you have got maximum amplitude all the time, when you have maximum, that's how you get this. It's possible to get this. Okay? In the presence of friction, it's possible to get this. But for you to get this, you need to keep on pushing that thing. The spring mass, as it's going back and forth, every time it comes, then it's going, you push it. Comes, goes, you push it. It comes, it comes, then it's going, you push it. So if you are pushing, then you can achieve this result, where the amplitude stays the same with time. And this is what is known as forced oscillations. Because the amplitude is very large, then you have a phenomenon which is known as resonance. Resonance occurs when the amplitudes of vibrations are very large. When something is vibrating very, very much, then you have a phenomenon which is known as resonance. So basically, yeah. So this is what it is.
You're breaking, can't hear you.
I was saying when something is vibrating with maximum amplitude, when a mass which is executing simple harmonic oscillation is vibrating with maximum amplitude, then we say that resonance is happening. Okay? And the frequency at which that happens is known as the resonance frequency. For you to have resonance, you need to apply a force. So you need to apply your force. The force you are applying should be at the same frequency as the frequency of the system. That's when you're going to have resonance. You'll be adding energy. The energy which was lost due to the friction, you'll be replacing it. As you apply a force, you are replacing the energy which was being lost due to friction. Therefore, in that particular case, you can afford to have maximum amplitude, hence resonance and resonance frequency. The frequency at which that happens, the resonance frequency. Okay, we have been this thing for 2 hours a bit, so I'm going to stop here. If you've got any questions, you're going to ask me. So basically, in a nutshell, we know that this thing works. So basically, tomorrow, 9:30, we are going to start our tutorials. I was sent tutorial questions. I think I will try to see where I put them. If I don't find them, I'll download them again. So basically, I'll stop the presentation. I also need to get home because I'm still at work. Okay, so I'll see you guys tomorrow when we start solving our tutorial questions.
Bye.
All right. Have a
Thank
good
you,
one.
sir.
Cheers.
See you tomorrow, 9:30.
Yes, at 9:30.